So this question is asking, when is a coset a subgroup? So it's going to be a subgroup if and only if A is already an H. So if you start with looking at cosets of H, where H is a subgroup, the only subgroup that you're going to get is a look at this. So here are the cosets of the symmetric group, S3, where H is this, and here are the cosets. You've got those two are equal and those two are equal, but this is the only subgroup. One way to see that is that the only place where the identity appears is in the two highlighted red ones. So those are the only two that have a chance of being a subgroup. And in fact, we picked it to be a subgroup, picked H to be a subgroup already. So this is what this theorem is saying, is that the only way to get a subgroup is to take the... So let's suppose, well, the identity has to be in there. There exists an H such that E is equal to H. Then A is equal to H inverse by definition, because HA gives the identity. So whenever you have that, that means that A must be the inverse of H because it gives you the identity. So that means we have it's an H. So that's good. So if HA is a subgroup, that means that A is an H. Direction. If A is an H, by a previous theorem, we get that HA is equal to H. Why is that? Well, what we have is that HA is equal to the set of all H such that H belongs to H. All right. Oh, but A is in H. So if I want to find any element of H called H naught, I can be able to achieve that by letting H. I can find an element of H that's multiply A by that. Well, the thing I want is HA inverse. So this is going to be my value of H, and that'll give me whatever H naught I want. Right? And this is an element of H by closure, because H naught is an H, and because A is an H, A inverse is an H. So that's an H by closure, and so we're going to be done. So we have a subgroup. HA equals H, a subgroup. And we're done. That's all there is.